Okay. Hi, everyone. I'm Edmund Chang, and my dissertation is on embodied carbon in buildings. So for my dissertation, I research about embodied carbon on an office building in Glasgow. The office building is shown here on the right. So as a summary, I'm going to be sharing about the carbon footprint of the construction industry globally here in Scotland and the UK. I will also be explaining my methodology, but I will not go too in depth. I'm also going to be comparing my results with other case studies and addressing the problem statement. Here's a solution that I have discovered in my project, and I'm going to tell you how. By increasing the height of the building by a little, we can save materials and reduce carbon footprint. But before telling you how I'm going to manage that, I will give a little insight into the current construction industry and how it affects the climate. In Scotland alone, the current measures put in place to mitigate climate change includes sourcing for nationally made materials whenever possible, or even better, locally made materials. Production of steel using renewable energy and using cement substitutes are also essential because production of cement generates a tons of carbon dioxide. There has also been talks to design buildings to last 100 years instead of typical 60 years, which by doing so reduces the need to build. So if we build nothing, there won't be any new construction adding on to the carbon budget. In the UK alone, the construction industry is the single largest contributor of CO2 at 49% of the total carbon emission. There is an urgency in decarbonization to limit the increase of global warming to only 1.5 degrees Celsius after 2050. If we do not enforce such strict carbon laws, the world's average temperature is projected to soar to more than 3 degrees Celsius by 2100. The world is expected to build more than 230 billion square meters of new construction by 2040. That is equivalent to adding on the city the size of Paris every week to the planet till 2050. And globally, the construction industry generates 38% of carbon footprint every year. But unfortunately, current trends have implied that it will still increase if countries continue to ignore strict warnings. And to make matters worse, most countries still do not have carbon regulations, especially developing countries. UK has set a target of achieving net zero by 2050, and Scotland has pledged to achieve it faster than the rest of the UK. The 2020 target was a near miss, but it was achieved thankfully to COVID-19, ironically because construction industries were put on the stop. There are currently 2.45 million homes in Scotland and more than 200,000 non-domestic buildings. Around 30% of homes and buildings still need retrofitting to meet climate change targets. But despite efforts to retrofit, we are still not meeting the targets fast enough. The UK alone has a 5-year carbon target that must be achieved in every 5 years interval so that we can achieve net zero by 2050, 5 years later than the target set for Scotland. However, similarly to Scotland, the UK's current reduction levels are not fast enough, and we are not on track to achieving net zero. So that's enough background information regarding the construction industry, and I'm going to introduce how civil engineers measure carbon footprint. In a building, its carbon footprint can be split into two major components, which are operational carbon and embodied carbon. Operational carbon associates with power and heat to operate the building, and embodied carbon covers the material extraction, manufacturing, and construction. Embodied carbon is the main focus for engineers currently because energy efficient buildings are on the rise. Buildings are transitioning to using renewable energy to power up the building, and the operational carbon emission will be negligible in the future. Embodied carbon, as a result, will comprise the entire life carbon of a building. So imagine a building with 100% clean energy. The yellow portion in this diagram will be non-existent. So this means that embodied carbon will occupy the whole life carbon of a building. So it's very crucial that we look into reducing embodied carbon. And what did I do for my project? I looked into an office building that is currently under construction and try to find a way to reduce embodied carbon for the structure of the building. For confidential reasons, I can't disclose the actual location of this building, but you can sort of guess where this is. What I can reveal is that this building has 13 floors, a rooftop running track, and it has glass and aluminum facade. This here is the structure model of the office building created using a computer software. The frame of the building is mainly steel, and it has about 3,500 tons of steel. My methodology for this project can be summarized in these steps. First, I exported all the materials to create the building from the computer software into Excel spreadsheets. Then I calculated the embodied carbon of the entire project in those spreadsheets. After that, to reduce embodied carbon, I changed some parameters in the structure of the building, did some trial and error in more computer software, and recalculated the embodied carbon. There are lots of numbers in my Excel spreadsheets, so I'm not going to show you, but if you're interested, you can email me later. So for my calculations, the steel frame of the building contributes the most embodied carbon, which is the orange pie shown here. Therefore, I'm going to focus on bringing down the embodied carbon in the structural frame of the building. The key findings for my calculations showed that the building generates about 19,000 tons of CO2 equivalent and about 580 kg of CO2 equivalent per meter squared. Approximately 3,500 tons of steel is required to construct the building. This table shows the comparison of my building against 15 other recently built buildings in the UK. And as you can see, the Glasgow office building sits below the average embodied carbon of 15 other office buildings. The Glasgow office building is 173 kg of CO2 equivalent per meter square, lower than the average value of 753. And I mentioned at the start that increasing the height leads to reducing carbon footprint, and I'm going to explain how. Currently, the Glasgow office building is capped at 60 meters. Part of the reason is due to saving cost and fire safety, but this is not the main issue as to why this building is limited to 60 meters. But let me address how increasing the height will lead to savings in materials and ultimately reduce embodied carbon. By removing the height restrictions, engineers can use a deeper beam, but it is, sorry, my lights went off. Okay. By removing the height restrictions, engineers can use alternate deeper beam sizes that has a lower mass per meter run of steel, as current beam sizes are shorter but thicker in width to compensate for the loss of strength. It is higher in mass per meter run as compared to beams that are deeper but thinner in width. To make things clearer, both sizes of steel shown here have the equal amount of capacity to hold certain weight, but one is taller than the other. The taller beam has a lower mass per meter run at 170 kg of steel per meter, but the shorter beam has 280 kg of steel per meter. By opting for the taller beam, we can save up to 50 kg of steel per meter per beam. So after switching to taller beams, the building will increase by 1.4 meters and will be standing at 61.4 meters high. As a result, as the taller beams are lighter, there is a huge saving of 167.5 tons of steel and an overall reduction in 220 tons of CO2 equivalent. As for the embodied carbon per meter square, it will reduce by 7.5 kg of CO2 equivalent per meter square. The 167 tons of steel saved can be instead used for production of 185 cars. And for the embodied carbon, it is similar to 223 return trips for one person from London to New York. Unless you are taking a private jet, then it will be very much higher. So I've covered enough numbers for the rest of the day, so I'm going to tell you the main reason why the building was restricted to 60 meters. This is because of the Glasgow City Council does not want tall buildings to ruin the historical city skyline that Glasgow is associated with. They are worried that some of the historical buildings and structures will not be visible on the Glasgow skyline, as these tall buildings will be the only ones visible from afar. This is a similar reason in Europe, and this is why we don't see lots of skyscrapers in Europe, unlike the US and Asia. This also contributes to the underlying issue relating to history versus climate change. People are concerned that retrofitting such old and listed historical buildings might suffer damage to their quality and character. And as a result, people are calling for the government to allow such historical buildings to be exempted from retrofitting to meet climate change targets. So I'm quite curious which option would most of you pick, preserving a piece of history and culture or mitigating climate change? And as a conclusion, I have found a possible solution to add on to current measures, which is by relaxing the height restrictions, at least in Glasgow City, we can save materials and ultimately reduce embodied carbon. Therefore, what future measures can the construction industry do? Well, as a start, engineers should not be over-designing structures so that more materials could be saved. All materials would also need to be recyclable, from the steel beams down to the bolts, so we are not creating more materials. Perhaps in a few years' time, engineers might discover a way to sequester carbon into the concrete or other green construction technology. But as a start, Scotland should start looking into focusing more on climate change instead of preserving too much of its historical buildings. But this may sound very controversial, but you can let me know what you guys think in the comments. Would you preserve a piece of history, or would you put into effort into mitigating climate change? And thank you. That's all I have for my presentation.
Edmund,